Welcome! In this video, we'll tackle problem number 125, valid palindrome. This is a classic problem that tests your ability to handle string manipulation and validate conditions efficiently. We'll explore different approaches to solve it and discuss their complexities. Let's dive in. In this problem, we're tasked with determining if a given string, S, is a palindrome. A palindrome is a sequence that reads the same backward as forward. However, for this problem, we only need to consider alphanumeric characters, ignoring spaces, punctuation, or any other non-alphanumeric symbols. Additionally, the comparison should be case-insensitive, meaning uppercase and lowercase letters are treated the same. The input will be a single string S, and the output will be a Boolean value, true if the string is a palindrome, and false otherwise. For example, if the input is a man, a plan, a canal, Panama, after removing non-alphanumeric characters and converting everything to lowercase, the string becomes Amanaplana Canal Panama, which is a palindrome. Therefore, the output is true for this case. Now let's look at another example. If the input string is race a car, after pre-processing, which involves removing non-alphanumeric characters and converting the string to lowercase, the result is race a car. This sequence does not read the same backward as forward, so the output in this case is false. There's also an edge scenario to consider, such as when the input string is just a single space character. Since there are no alphanumeric characters present, this is treated as an empty string, which is considered a palindrome. So for the input, the output would be true. It's important to note some additional details about the constraints and rules for this problem. First, the input string will only contain printable ASCII characters, and its length can range from 0 to 100,000 characters. A string is considered a palindrome if it reads the same backward as forward after pre-processing. Pre-processing involves keeping only alphanumeric characters and ignoring spaces or punctuation, as well as treating uppercase and lowercase letters as equivalent. For example, the string ABBA would still qualify as a palindrome due to its symmetry, even though it contains mixed cases. Additionally, an empty string or a string consisting only of spaces or non-alphanumeric symbols is always considered a palindrome. Finally, let's address a specific edge case, strings with no alphanumeric characters. For instance, if the input string contains only symbols like, the pre-processing step would result in an empty string. Since an empty string is considered a palindrome by definition, the output in such cases would be true. This ensures that the solution comprehensively handles all possible edge cases, including strings with varying characters, mixed cases, or no alphanumeric content at all. To solve the problem of determining whether a string is a valid palindrome, we can consider several approaches. The first is the brute force method. Here, the idea is to filter the string by removing all non-alphanumeric characters and converting everything to lowercase for consistency. Once the filtered string is prepared, we check if it's a palindrome by comparing it to its reversed version. This approach is straightforward, as it uses basic string manipulation techniques and is easy to implement. However, it does require additional memory to store the filtered string and its reverse. While the time complexity is O(n), because we process the string once for filtering and once for reversing, the trade-off is in the extra space usage, which may become significant for larger strings. A more efficient solution is the two-pointer technique. This approach avoids the need to create a new filtered string altogether. Instead, we use two pointers, one starting at the beginning of the string and the other at the end. These pointers move toward each other while skipping non-alphanumeric characters. At each step, we compare the characters they point to, ensuring they match. If a mismatch is found, we can immediately return false. Otherwise, we continue until the pointers meet or cross, indicating the string is a palindrome. This method is highly efficient, as it processes the string in a single pass with O(n) time complexity, and it uses constant space since no additional data structures are needed. While it requires careful handling of edge cases, such as empty strings or strings with only special characters, it strikes an excellent balance of performance and memory efficiency. Another approach to consider is the recursive method. This technique uses a helper function to compare characters from the start and end of the string, adjusting the pointers to skip non-alphanumeric characters. The base case occurs when the pointers meet or cross, at which point we return true. If the characters at the pointers don't match, we return false. Otherwise, we make a recursive call with updated pointers to continue the comparison. While this method provides a clean and elegant solution, it has significant trade-offs. Specifically, each recursive call adds to the call stack, leading to O(n) space complexity in addition to the O(n) time complexity for traversing the string. This makes it less practical for large strings, as it risks stack overflow in real-world scenarios. Despite its elegance, the overhead of recursion makes it a less efficient option compared to the other techniques. Among the approaches considered, the two-pointer technique is the most effective and practical solution. It achieves optimal performance with O(n) time complexity and O(1) space usage by processing the string directly without creating additional data structures. This method leverages the symmetric nature of palindromes, comparing characters from the outer edges inward while efficiently skipping non-alphanumeric characters. Case insensitivity is handled seamlessly by converting characters to lowercase during the comparison process. While the brute force method is simpler to implement, it requires extra space for the filtered string and its reverse. Similarly, the recursive approach, although elegant, is less efficient due to its high space usage and potential stack overflow issues. Therefore, the two-pointer technique stands out as the best choice, offering a robust solution that is both space and time efficient, particularly for handling larger inputs and edge cases effectively. To solve the problem of determining whether a given string is a valid palindrome, the first step is pre-processing the string. This involves removing all non-alphanumeric characters and converting all letters to lowercase. This step is crucial because spaces, punctuation, and other special characters should not affect the palindrome check, and converting to lowercase ensures that case differences are normalized. For example, if the input is a man, a plan, a canal, Panama, the result after pre-processing becomes Amanaplana Canal Panama. This cleaned version of the string is what we will use for further analysis. Now that we have a clean string, the next step is to apply the two-pointer technique. This involves using two pointers, one starting at the beginning of the string, called left, and the other starting at the end, called right. This technique works because a palindrome reads the same forward and backward, so comparing characters at these mirrored positions will determine if the string is valid. As the pointers move inward, left increasing by 1 and right decreasing by 1 after each comparison, we can efficiently check the entire string. For instance, with the string Amanaplana Canal Panama, the pointers start at index 0 and index 20. Each pair of characters is compared, and if all matches are valid, the string is a palindrome. Once the two-pointer comparison is in progress, the loop continues as long as the left pointer is less than the right pointer. At each step, the characters at the two-pointer positions are compared. If any mismatch is found, we can immediately conclude that the string is not a palindrome and return false. However, if all character pairs match, the loop finishes without issue, and we return true because the string is indeed a valid palindrome. This approach is efficient, as the algorithm stops as soon as a mismatch is detected, avoiding unnecessary comparisons. Additionally, edge cases like an empty string, single character strings, or strings containing only non-alphanumeric characters are inherently handled. They are always considered valid palindromes after pre-processing. For this algorithm, we rely on a few key data structures. The clean string is central to the palindrome check, and while strings in Python are immutable, we can use a list or generator during pre-processing to construct the cleaned version efficiently. Another critical component is the two pointers, left and right, which are simple integer variables. These pointers are used to track indices for character comparison, minimizing space usage and avoiding the need to create a reversed copy of the string. This design keeps the implementation both efficient and straightforward. Analyzing the algorithm's complexity, we find that it is very efficient. The pre-processing step, which involves filtering and lowercasing the input string, has a time complexity of O(n), where n is the length of the input. The palindrome check, which uses the two-pointer technique, also runs in O(n), as each character is compared at most once. Therefore, the overall time complexity is O(n). For space complexity, the pre-processing step creates a new string, requiring O(n) space. The two pointers, however, only use O(1) space. Thus, the overall space complexity is O(n), primarily due to the creation of the clean string. Let's walk through a concrete example to tie everything together. Consider the input string a man, a plan, a canal, Panama. First, during pre-processing, we filter out non-alphanumeric characters and convert everything to lowercase, resulting in the string ammonoplanic and alphanuma. Next, we apply the two-pointer comparison. Initially, indices 0 and 20 are compared, both are a, so the pointers move inward. Then indices 1 and 19 are compared, which are both m, so again the pointers move inward. This process repeats until the pointers meet at the center, with all comparisons matching. Since no mismatches were found, the function returns true, indicating that the input is indeed a valid palindrome. This solution efficiently checks whether a given string is a valid palindrome. It consists of two main steps. 1. Pre-processing the input string. The code uses a generator expression within the join function to filter out non-alphanumeric characters. For each character in the input string s, it checks if the character is alphanumeric using the char isalnum method. If the character is valid, it converts it to lowercase using char lower. This results in a cleaned-up version of the input string containing only lowercase alphanumeric characters. 2. Palindrome check. The solution compares the clean string filtered _chars with its reverse, filtered _chars, ::-1. The slicing operation, ::-1, efficiently reverses the string. If the original string and its reverse are identical, the function returns true, indicating the string is a palindrome. Otherwise, it returns false. This approach is both clean and optimal. It processes the input string in O(n) time, where n is the length of the string, and performs the palindrome check in another O(n) time. The overall time complexity is O(n), and the space complexity is also O(n), due to the storage of the filtered string. The solution handles all edge cases, including strings with only non-alphanumeric characters, returning true for an empty string, mixed case characters, and valid palindromes with spaces or punctuation. This is the Java implementation of LeetCode problem number 125, valid palindrome. The logic mirrors the Python implementation by pre-processing the input string to retain only alphanumeric characters and convert everything to lowercase. Java-specific differences include using the string builder class for efficient string manipulation and iterating through the string with a for loop. The palindrome check is performed using a two-pointer approach to compare characters from both ends of the filtered string. This ensures an efficient O(n) time complexity. To begin solving the problem, we start by pre-processing the input string. For the first example, the input is a man, a plan, a canal, Panama. The goal of pre-processing is to remove all non-alphanumeric characters and convert the remaining characters to lowercase. This can be efficiently handled using the generator expression shown here, which iterates through each character, keeping only alphanumeric ones and transforming them to lowercase. For instance, the first character A is alphanumeric, so it gets converted to a. The space is skipped since it's not alphanumeric, and the next character M is kept as is because it already meets the criteria. This process continues for the entire string. By the end, we are left with the filtered result, ammonoplanic and alphanuma, a compact version of the input containing only the necessary characters in lowercase. Now, this process string is ready for the next step, where we determine if it is a palindrome. In this step, we determine whether the process string is a palindrome. A palindrome reads the same forwards and backwards, so we compare the string to its reverse. For the process string ammonoplanic and alphanuma, we calculate the reverse using slicing with ::-1, which gives us the same string, ammonoplanic and alphanuma. Since the reverse string matches the original, we can confirm that the input is a valid palindrome. The function then returns true, as indicated in the output. Now, let's move on to a second example with a different input to see how the solution handles other cases. The second example uses the input race a car. Just like before, we pre-process the string by filtering out non-alphanumeric characters and converting the rest to lowercase. As we go through the string, R, A, C, and E are kept, while the space is skipped. The process continues until all valid characters are collected, resulting in the filtered string racecar. Now, we proceed to check if this string is a palindrome by comparing it to its reverse. The reverse of racecar is rexisor, which does not match the original. Since the two strings are different, the function returns false, indicating that the input is not a valid palindrome. Finally, let's look at a special case to understand how the solution behaves with minimal input. In the third example, the input is a single space. During pre-processing, we filter out all non-alphanumeric characters. Since the input contains no valid characters, the result is an empty string. By definition, an empty string is considered a valid palindrome because it reads the same forwards and backwards. When we compare the empty string to its reverse, they match, so the function returns true. This demonstrates that the solution correctly handles edge cases like empty strings, ensuring robust results for all inputs. To understand the time complexity of the is_palindrome function, let's break it down step by step. First, the operation that filters and lowercase the characters involves a generator expression. This expression iterates through the string s one character at a time, checking whether each character is alphanumeric and, if so, converting it to lowercase. Since both the char iselnum, check and the char lower operation are constant time operations, the overall complexity for this step is O(n), where n is the length of the string. Next, the .join function creates a new string from the generator's output. This requires iterating over all n characters again, making this step O(n) as well. Finally, the string reversal operation, which uses slicing with filtered underscore chars, ::-1, creates a reversed copy of the string. If the filtered string has m alphanumeric characters, this step takes O(m) time. These steps form the foundation of the overall time complexity analysis. After filtering, joining, and reversing the string, the final step is the string comparison. Here, the function compares the original filtered string with its reversed version using the == operator. This operation compares the strings character by character, taking O(m) time in the worst-case scenario where all characters need to be checked. Combining all these operations, the total time complexity is the sum of O(n) for filtering and lowercasing, O(n) for joining, and O(m) for both reversing and comparison. This simplifies to O(n) plus 2m. However, since m, the number of alphanumeric characters, is always less than or equal to n, we can simplify the overall time complexity further to O(n). This highlights the efficiency of the implementation when processing even very large strings. Now, let's consider the space complexity of the function. The first major contributor to space usage is the new string filtered underscore chars, which is created by the .join function. In the worst case, if all characters in the input string are alphanumeric, this string requires O(n) space. Similarly, the reverse string created by filtered underscore chars, ::-1, also requires O(m) space, where m is the number of alphanumeric characters. Since m is at most equal to n, this step also requires O(n) space in the worst case. On the other hand, the generator expression used for filtering is lazy and does not store all characters in memory simultaneously, contributing only O(1) space. Combining these, the overall space complexity is dominated by the storage of the filtered and reverse strings, making it O(n). This balance between time and space highlights the thoughtful design of the implementation. To compare, a brute force approach could process the string by checking characters one by one from both ends, skipping non-alphanumeric characters as needed. This method would achieve O(n) time complexity for traversal but could do so using only O(1) space if no additional strings are created. However, such an approach would involve more complex logic, as it would need to handle conditions to skip non-alphanumeric characters in real time. In contrast, the current implementation simplifies the process significantly by pre-processing the string. While it uses O(n) extra space to store the filtered and reverse strings, this trade-off leads to cleaner, more maintainable code while maintaining the same O(n) time complexity. This makes the optimized approach a practical and efficient solution for the problem. Finally, let's validate the big O analysis for both time and space complexity. For a string with n characters, the filtering and lowercasing step takes O(n), as does the joining operation. The reversal of the filtered string takes O(m), where m is the number of alphanumeric characters, but since m is always less than or equal to n, this simplifies to O(n). Similarly, the string comparison step also takes O(m), which is at most O(n). Adding these together confirms the overall time complexity is O(n). For space complexity, the filtered string and its reversed version dominate the memory usage, each requiring O(n) space. Thus, the total space complexity is also O(n). These calculations reinforce the efficiency and scalability of the current implementation for validating palindromes. When solving this problem, there are several common pitfalls to watch out for. One major mistake is ignoring non-alphanumeric characters when checking for palindrome properties. The problem clearly states that these characters should be excluded, so failing to pre-process the string can result in incorrect results. For example, a man, a plan, a canal, Panama is a valid palindrome only when non-alphanumeric characters are removed. Another issue is case sensitivity. If you compare characters directly without converting them to the same case, uppercase and lowercase letters like at and a will be treated as different, leading to errors. Lastly, overusing space by creating extra structures, such as a separate string or list to store filtered characters, is inefficient. This approach increases space complexity unnecessarily, even though the problem can be solved in place using 2 pointers, which is far more optimal. Another challenge arises from incorrect 2-pointer logic. This can happen when pointers are not managed correctly, such as failing to skip over non-alphanumeric characters or mishandling edge cases. Errors like infinite loops or premature termination often stem from this. Speaking of edge cases, these are another area where mistakes are common. Inputs such as empty strings, single character strings, or strings containing only non-alphanumeric characters all need special attention. For instance, an empty string or a string with just symbols should return true, as they technically meet the criteria for being palindromes. Overlooking these scenarios can lead to incorrect results, so it's crucial to handle them properly. To excel in interviews, it's helpful to understand key insights about string manipulation problems. The 2-pointer technique is a highly efficient approach that simplifies problems like this one and is often expected in interviews. Also, problems involving steps like ignoring certain characters or normalizing input typically require pre-processing, such as filtering out unwanted characters or converting the case. While building a filtered string and reversing it is a straightforward solution, many interviewers prefer in-place techniques that use minimal space. Additionally, clear communication is critical. Make sure you explain how you handle edge cases, filter alphanumeric characters, and normalize the case. This demonstrates logical reasoning and attention to detail. To further prepare, you can explore related problems like longest palindromic substring, valid palindrome 2, palindrome linked list, and palindrome permutation, as they build on similar concepts. Now let's compare a few alternative approaches and their trade-offs. The 2-pointer technique is a popular method. It works by using 2 pointers that move inward from the start and end of the string, skipping non-alphanumeric characters and comparing them case-insensitively. This approach is efficient with O(n) time complexity and O(1) space complexity, but it requires careful attention to pointer movement. Another option is to filter the string and reverse it. You create a new string containing only alphanumeric characters, normalize the case, and then check if it matches its reverse. While this method is simpler to implement, it uses O(n) space, which can be a disadvantage in memory-constrained scenarios. Finally, there's the recursive approach, where you recursively compare characters at the start and end while skipping non-alphanumeric ones. While intuitive, this method also uses O(n) space due to the recursion stack, making it less suitable for very large inputs. Each method has its strengths and weaknesses, so choose based on the specific constraints and requirements of the problem. Great job! Today, we explored the valid palindrome problem, broke it down into efficient solutions, and highlighted key concepts to remember. Keep practicing, and don't forget to apply these techniques to similar problems in your coding journey. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!